Okay, so today we're gonna finish up where we left off last week, talking about system modeling. So you remember that there's two inputs to validation algorithms. One is a model of the system, and the other one is a property specification. So last week we talked about the first one, which was modeling the system. We didn't quite finish, so we're gonna finish that up today. And then we're gonna move on to the second input, which is the property that we want the system to satisfy. And so before I get into that, I just wanted to really quickly kind of zoom out for a second here. And just kind of give you a concrete example to kind of have some context in your mind for what we're thinking about when we're building models. Because I know it can get kind of easy to get lost in the math. So I just want to quickly provide this kind of concrete example where if you're getting lost in the math, you can try to think back to this and kind of ground the things that we're learning. So we're in the Aero department, so I'm going to go ahead and try to use an aircraft. They don't teach you to draw aircraft when you get your master's and PhD in the Aero department, but that's the best I can do. So we're going to assume we have this aircraft kind of flying along, and it's changing altitude every so often, and this is the ground here. And we're going to assume, so if we were going to model this aircraft, we would need to model its decision making, we would need so its agent, its sensor, and then also its environment. Let's just think about the sensor, and let's think about like one part of its state. So let's just think about a sensor that's responsible for measuring its height above the ground or its altitude. And so as we go along, we'll get different measurements of this height, something like this. And they're kind of some noisy version of the actual height. So these are our observations. When we talk about data, this is the observations that we're getting. This is the data that we're getting. And then let's assume also that for this kind of data collection run in the real world, we also had this really, really expensive, super good, super accurate altitude sensor that we ran along with it that basically gave us kind of the ground truth. So what was the actual height that we're at? And so then we can get these pairs that are like H and H hat, where H hat is going to be that measured version and H is the ground truth version. So we can have H1, maybe we have H2, and so on, all the way to M data points. And so in this case, our state is H, and our observation is H hat. And so what we can do is we could then maybe make a plot where on the x-axis we plot H, and on the y-axis we plot H hat, and it will probably look something like this. And what we're trying to model is our observation model, which we said is the probability of getting a particular observation given that we're in state S. So in this case, our observations are these H hats. So probability of observing H hat given that we're at height H. And so the first thing we need to do, which we talked about last time, is select a model class. So what is a good model class to kind of represent this data that we see here? And to me, I don't know, it kind of looks like the H hat is a linear function of H with some noise added to it. So that indicates to me that maybe a conditional Gaussian model is a good idea here. So we're going to model as a conditional Gaussian, where we say H hat comes from some function parameterized by theta of H with some noise added to it. And then I said I think it looks kind of linear, so I'm going to take it one step further and say that's a linear function. So we'll say theta 1 times H, so that'd be the slope of that line, plus theta 2, and then this sigma squared. And so now we have our model class, and if you remember the second step was to then perform some sort of optimization to pick these parameters. So last time we learned about maximum likelihood optimization. And then that would give us some values for the parameters. So to me, this looks kind of like a slope of 1. So we'd probably get something like theta 1 equals 1. Theta 2 is probably 0. The y-intercept's around 0 here. And then our sigma squared is like some value, maybe say like 0.05. Okay, and so that's kind of what I want you to be thinking of when we're talking about taking data and fitting a set of parameters to that data and selecting model classes. And then just kind of one more thing here. let's say that we instead collected a bunch of data here, and it looked maybe sort of like that or something. Okay, so this doesn't look linear anymore. First of all, you should think about what you're doing. If this is what your altitude sensor looks like, you might just want to throw it in the trash, because this is probably not the best plan. But say you do want to use the sensor and you do want to model it. To make a model of the sensor, you probably don't want to select kind of a linear model here anymore. And so you're going to need this kind of more expressive model class, which is what I was talking about last week. So hopefully this kind of just helps ground all the things we've been talking about. What questions do you have on this example? Yeah.
Is that the delta, or what did you write on the second line? Right after
this line?
Straight.
Which line?
Oh, what's the letter that you wrote?
Here?
Yeah.
Here?
Yeah.
That letter? Theta.
Is that the, or what's the thing right next to it?
F. Here, this is supposed to be F, theta, H. Yeah, always let me know if you can't read my handwriting. Okay, cool. So let's back up where we left off last time. So if you remember, we had talked about how I'm super indecisive. And so for that reason, I really like Bayesian parameter learning, because then we don't just have to pick one set of parameters like we did with maximum likelihood parameter learning. And instead we get to kind of maintain this distribution over all possible parameters. So we talked about how we can do that, and it turns out we want to model this p theta given d, but we don't know how to compute this directly. And so we said, what's nice is that we do know how to compute PD given theta, and in fact that's actually what we needed to do for the maximum likelihood parameter learning, so we talked about how to do that. And then we said, okay, well if we can only compute PD given theta, we need to use this thing called Bayes' rule, so we derived that from the definition of conditional probability. Thanks for pointing out this typo last time, it should be fixed now. And so we derived Bayes' rule, and then we said, okay, let's take this and apply it to our p theta given d, and we got this expression here. And we kind of examined this further, and we said, okay, this expression has what we call a likelihood model, which is exactly what we were optimizing in our maximum likelihood parameter learning. And then it has this extra term, p theta, which is a prior. So this is something we didn't have with maximum likelihood parameter learning. Here we're specifying what is kind of our belief before we see any data over what possible values are the likely values for the parameter theta. So I gave the example if someone handed me a quarter and they said, what's the probability that this quarter comes up heads? I'd have this kind of strong prior that assigns a lot of likelihood to theta being 0.5, or like 50% being the probability or chance that it comes up heads. Then we observe some data and we update our belief over the probability that it becomes heads, and we get this thing called the posterior distribution over theta. But then I told you that we have this problem where, so that was the discrete case. We also have the continuous case where we have kind of the summation in the bottom turns into an integral. But regardless of the expression we have, it's generally quite difficult to compute this result analytically. So when we have the summation, the number of terms in the sum scales exponentially with the dimension of theta. In this continuous case, computing this integral can be quite difficult analytically. And so a lot of times we can't actually just get kind of an analytic function for these values, or for these quantities here. But there is something that's kind of cool, which is, so it's really hard to compute this because we need to compute it for every single value of theta. So we need to sum up over all possible values of theta, we need to integrate over all possible values of theta. But if I just give you one value of theta, we can compute this numerator. It just involves computing PD given theta, which we did for our maximum likelihood estimation, and then it involves plugging theta into our prior distribution to get the value out. So what I'm trying to say is we can compute this numerator. And what's kind of cool is through this thing called probabilistic programming, we can actually then draw samples from the posterior. So we can get samples that look like the posterior distribution over theta. So here's how we do this. I'm not going to dive too deep into how probabilistic programming works, but But the good news is that later in this course, we actually are going to dive into how it works. It uses a method called Markov chain Monte Carlo, which we'll talk about more when we talk about sampling from a failure distribution. But for now, you're just going to have to take my word that probabilistic programming can take evaluations of that numerator and draw samples from the posterior. So I don't want you to get like too bogged down with the syntax here. But essentially what's going on is we have our Bayesian parameter estimator. We input our likelihood model. So again, it needs to be able to compute the terms in this numerator. So we tell it how to compute this one. We input our prior distribution. So that's this part here. Then we input a sampler here. And this is, so there's a really cool package in Julia called Turing.jl. It does this probabilistic programming stuff for us. It has lots of different methods implemented. Super amazing package. If you're interested, definitely check it out. We input just one of the types of samplers. They have many different types of samplers that all could sample from this posterior, some with various pros and cons. And so we pick one of those, and then we say the number of samples that we want to draw from the posterior over theta. And then what we can do is actually just call this fit function, where first it just extracts some data. This is the whole probabilistic programming part. And so what's cool here is we don't actually draw samples in this function. We just say theta comes from this prior. So we say theta is sampled from this prior distribution. And then for each of our data points, we say that the y value of the data point was generated via our likelihood model. And this is enough to tell Turing what to do in order to actually get samples from the posterior. So again, this might seem like a little bit like magic to you. It probably should, because if you don't know the inner workings, it's hard to see what's going on here. But what I really want you to grasp here is just that if we can compute this numerator, which we can many times, then we can draw samples from this posterior. So I want to show you what this looks like, because I think it'll help kind of clear up what's going on. So you can imagine that we have, we were trying to learn the parameters for this model. And by the way, I figured out the case of the missing axis labels. There's like an issue with LaTeX displaying properly that I thought I fixed, and then realized 20 minutes before lecture that I didn't actually fully fix. So we're digging into that, but sorry, these are still supposed to have labels, and it'll be fixed soon. But either way, let's imagine that we're trying to learn the parameters of this model we were learning before. So we have this theta 1, theta 2, theta 3. And again, if you want to have an example in your mind, you can think back to that example where we're trying to estimate the sensor model for that aircraft that I showed at the beginning. And so it turns out what we can do is just specify a prior distribution over these parameters. So we're going to say we don't really know what the parameters are. We don't have a good idea ahead of time. And so the prior distribution is just going to be a big multivariate normal distribution centered at 0 with kind of this big variance to say, like, we give kind of an equal likelihood to many different possible parameters. Then we need to define this sampler, which is what I was mentioning. You don't need to know what this is right now. A very popular sampler, though, in probabilistic programming is the no U-turn sampler, or NUTS. And then we'll say how many samples we want to draw. So we want to draw 1,000 samples of data. And so then we can just run this sampling. It does it for us. You see it kind of ran this sampling. And we can see what comes out. So again, the axis labels are missing. I apologize for that. But you can see this is samples of theta 1. So if you look back to our maximum likelihood estimation, we thought theta 1 was around 0.999. Theta 2 was around 0, and theta 3 was around 0.05. So you can see here our expected value using these samples is 0.98, so we're pretty close. But now we have a full distribution of possible values for theta rather than just one value. And so for theta 1. Similarly for theta 2, it's centered at 0, so it's centered at kind of what we thought it would be. But again, we have this full distribution over possible values. And then similarly for the variance. But one thing that I did here is I actually only gave it 20 randomly sampled points of these like pink points here. So I can give it more than that. So I'm going to give it maybe 100. What do you guys think would happen when I increase the number of data points that I give it to estimate these parameters? What would happen to the posterior distributions? Get smaller. Yeah, exactly. So more data we have, the more confident we should be that we are getting the right parameters. And so ideally those distributions should shrink. So let's try that. Okay, looks like it's running. Didn't shrink yet. Give it a second. There we go. Okay, so hopefully you remember what they looked like before. They're a little bit smaller now. So we're more certain. We now have an expected value of 1 still, but our distribution is a lot smaller because we have more data points, and so we're more confident in our estimates of the parameters. Maybe for fun, let's just do 200 data points just to drive this point home. And while that's running, what questions do you guys have on this? Yep.
So I think I'm just a little bit confused about the likelihood model. So you made the example before with the airplane. Would that be an example of how you obtain the likelihood model also in real life, or how can I think about that?
Yeah, that's exactly right. So in that case, the likelihood model would be that like normal distribution that we had that was like saying that y was generated by applying, or h hat was generated by applying some function to h and then adding some noise. And so if you see, let me go back here really quick. So if you look at this part of the algorithm here, what we're saying is our yi would be that h hat, our xi is h, and we're saying our likelihood is some function that we've implemented that takes h, in our case it was like apply a linear transformation, takes h, and then also adds some noise to it. So it adds like a Gaussian distribution or something like that. And that's how we generate our measurement, or our h hat.
Okay, but in like that relies on the fact that you have like a sensor that you trust very much.
Yes.
Like your difference. Is that how it's done in real life as well, or?
Yeah, that's a great question. So the question was like, okay, so you need to then have known both h, like the true value, and the h hat. So how are you going to do this? Yeah, you're exactly right. So you need to have a sensor that you already trust. That's one option. There's various ways to do it. Like one example could be like, I know for GPS, depending on, how much money you pay or how expensive your GPS is, sometimes you can get, like centimeter accuracy, but that's quite expensive. You probably don't want to run that on all of your maybe aircraft you're designing or something like that. And so you'll run the test with that really expensive one just for that one time to see how good your less expensive one is, and then you can build that model of the less expensive one using that data. But yeah, good question. You've definitely identified like a key challenge in creating these models. Are there any other questions? Yeah.
I don't think I'm fully understanding like how we're kind of ignored the denominator. Yeah, is this just like, I guess when we create that distribution, is that to create like the left side of the equation, kind of?
So it's creating.
What's this distribution?
We're drawing samples from this distribution. So we're drawing samples of theta given the data that we have. We don't get to know the density of it. So if we could actually compute this denominator, we could compute this exact function. It turns out all we can do is draw samples, and I haven't really told you how that works. So if that's kind of fuzzy in your mind, that's okay. We'll talk more about that later in the class. Yeah.
I guess this may be a syntax question, but I'm trying to understand, what does it mean for us to, are we asserting that yi comes from this distribution given that we passed in y to this function posterior, or? Essentially, can you explain the syntax a little bit more?
That's exactly right. So it's kind of, this is like the beauty of probabilistic programming, is we basically just say what distribution everything comes from, and then it's going to make those assumptions. We're saying these are our assumptions, and it's going to draw from the posterior. So this little symbol here, we're just saying theta is distributed according to this. That's the one we're going to sample. And we gave it a bunch of y's and x, and we're saying we're making the assumption that y came from this distribution.
The same syntax if the variable is not named will be like assumed, like it's sort of like postulated, and then if the variable is named is sort of the information that Turing uses to actually make that decision.
Yep.
Like in this case, we aren't passing in theta, but we are passing in y.
Exactly, yeah. And there's like some more nitty-gritty details of how the programming language works that I would recommend you check out some tutorials for, but that's the gist of what's going on. You have things that you pass in, and you're now making assumptions of how they're distributed, and then it's going to sample from all the rest. Yep.
So the sampling is an approximation of the actual density that's represented by the denominator.
Yep, that's exactly right.
Thank you.
The question was, the sampling is an approximation of the actual density here, and that's true. Okay, awesome. So let's go to the next part. Okay, so we just told you, sometimes we just get to draw these samples, that's all we can do. Sometimes though, it is possible to actually get an analytical solution for this posterior. Okay, so we're gonna do, finally, the frisbees. We're gonna do a little experiment. I don't really want this volume. Oh well. All right, well, we're gonna do this thing where we flip frisbees, kind of like that guy is doing there. And so I'm gonna turn that off for now. But basically every week, oh, by the way, every week our lab plays frisbee on Wednesdays at 4 p.m. at Robley Field if anyone wants to join. All skill levels welcome. But typically to start out, to decide who's on offense and which side of the field everyone's gonna start on, instead of flipping a coin, we flip frisbees. Typically we have two people stand and they flip frisbees, and then if they land in the same, someone calls same or different, and then we see if they land in the same direction or a different direction. And I kind of have this hypothesis that they're more likely to land in the same direction. So we're gonna test that out today. And so we're gonna learn this parameter that we call theta, which is gonna be the probability that both frisbees land facing the same direction. So then 1 minus theta is the probability that the frisbees land in different directions. We're gonna then wanna collect some data. So let's say we collected this data where we did 10 flips and we got these results. So they landed same, different, same, different, 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 so on. So we're gonna summarize this by saying n is the number of times that they landed facing the same way up. And then m is just the total number of times that we flipped the frisbees. So then if we want to compute PD given theta, that's going to be theta to the n. So theta is the probability that they landed in the same direction once. The probability that happened n times is going to be theta to the n. And then the number of times that they landed in different directions is going to be m minus n. And so 1 minus theta is the probability they land in different directions. So the probability that happens m minus n times is 1 minus theta to the m minus n. This is actually called a binomial distribution. And it turns out that if we, so this is our likelihood model. This is P d given theta. We also need to select P theta in this case. And so it turns out that if we select our prior distribution to have this form, called a beta distribution with these two parameters that we call alpha and beta, we'll get some more intuition in a second for what those are. Our posterior distribution is also a beta distribution. So we get this new beta distribution where these parameters are updated using these counts m and n. And again, we'll get more intuition in a second for what those look like. But to summarize, here's what happened. So we're trying to estimate this parameter theta, which is the probability of both frisbees landing in the same direction. We say n is the number of times that they landed in the same direction when we took our data set. We started with some prior distribution over theta, and it turns out if we have a prior of this form, we actually can analytically compute the posterior, and specifically it has that form. What questions do you have there?
When you introduced the binomial distribution on the previous slide, I'm wondering, I'm familiar with the probability mass also including the summation over, or not summation, sorry, some combination. I think it's like m choose n in front, so I'm wondering, is that necessary for the posterior distribution to be computed as we see on the next slide?
That might be the case. It's at least proportional.
If it's okay, I'll yield this one. That's the probability of hitting that exact sequence. If you just want to figure out the probability that you get n the same out of m flips, then you need the n choose whatever equation things.
Yeah, nice. I'll just repeat that for people online. So this is the probability that we got this exact sequence. If we just wanted the probability that like 5 of them were the same or n were the same, then we would need this like extra combination term in the front. Okay, so just a few notes. I skipped over this actual calculation. So if you're like, where the heck did this beta thing come from? No worries. You can either trust me that it's true, or you can check out chapter 4 of algorithms for decision making. It's derived there. Okay, so it turns out we had this thing where I said, this is our likelihood model, it's binomial. This is a beta distribution, and if we have a beta distribution with this likelihood model, then the posterior that we get out is also a beta distribution. And it turns out this actually happens a lot, and so there's the name for this, which is the conjugate prior. So we say that the beta distribution is the conjugate prior for a Bernoulli distribution, meaning that the posterior distribution is in the same class as the prior. Okay, so let's get some intuition here. Okay, so we're gonna try to test this out. I need 6 volunteers. Okay, Mykel, do you want to demonstrate how to flip a frisbee?
Yes.
Okay,
Ready?
go for it. Okay,
There we go.
so that landed,
Up.
I don't know, I actually don't know how you do it. If that one also lands in that way, we'd say that's the same, okay?
Ooh.
Okay, great, so it did.
Oh, yeah.
So that's the same. So we're starting here with this prior distribution, that's this beta 1, 1. This is kind of the most uniform prior you can start with. So we're saying this is essentially a uniform distribution, all possible values of theta between 0 and 1. Again, sorry, the axis label isn't here, but the axis label is theta. So we have equal probability for all possible values. So we're just saying we're totally naive. We don't know what this probability value is. We did just observe that we got one that landed the same. So we'll update this. And so we get this new posterior where we added the number same to this alpha term in beta. Oh no. Oh no, okay, we're good. live demos. Okay, so we get this new distribution. There's kind of a few interesting things we can think about here. So now we have 0 probability that the probability that they land the same is 0, right? Because we just saw it happen. So there's no way that theta is equal to 0, okay? So this is kind of our new distribution over these probabilities. Okay, do you two want to flip? Okay. Oh, different, okay. So we'll enter that one in. Guess we'll get an error every time we do this. Okay, so now there's 0 probability that the probability of them being the same is 1, because we've seen both things happen, and we're thinking most likely it's probably around 0.5, but we got this kind of wide distribution around it. Okay, so now I'm going to ask you guys all to go ahead, just with your partner, flip 10 times, and remember how many for each.
Okay.
Okay, go for it.
Yours.
You didn't remember.
Okay.
0, 2.
I think we're skewing the stats. Wow.
We're so
We might have
0, 4.
Okay.
0, 5. What the hell?
Oh man, that's crazy.
Okay, 1, 5.
3, 5.
It's weird frisbees.
2, 5.
Easier to count. I want to see how you're doing
4,
this.
6.
Cool.
We did it.
2, 6.
We got one.
That's funny. I feel like
4, 6.
4, 6, okay.
We're 4, 6,
Four,
7.
No, it's
4,
3, 7, yeah.
4 same.
Okay.
Okay. Alright. So we had one that was 4 same and 6 different. Alright. So now we're actually thinking that probability same is a little less than 0.5, so I guess my hypothesis isn't looking so great. Alright. What was your guys'?
we had 8 different 2 same.
Oh wow, okay. 2 the same
We're very different.
and 8 different. Okay.
No, 3 seconds. 3 seconds. 3 seconds.
So now we're like actually feeling pretty confident that it's lower than 0.5. All right, oh wait, I should have been adding these. What was I doing here? All right, can I get your numbers again? 4, 6, so 4 plus 2, 6. And then you had 8 different and
How many different ones?
6 different.
6 different. So 14. All right, whoops. Okay. Still think we're going to be pretty confident it's different. All right, and then the last one.
3 and 7.
3,
same.
same.
7.
Wow, okay. 9 and 21.
I've always been saying same too. No wonder I always lose.
I feel like it should be same.
I feel like it should be same.
I think I heard your hypothesis and I've been using it.
Well, all right, here you go. Now you've got the strategy if you need it. All right, thanks, guys. You can come get candy for me after lecture. All right, thanks for your participation there. So we've now ended up with this distribution where we have this distribution over the probability that they come up same. So it looks like we actually kind of feel like it's around 0.3 that they're the same, but we have some kind of bound. So my hypothesis of same being more likely, there's still some chance there. And actually what's cool is now that we have a distribution, we can like do things with it. Oh, I guess that clicking doesn't work. So we could actually look, I thought this was going to be a bigger area here, but we can actually look at like what is the probability that it's greater than 0.5 by looking at this distribution and finding the probability mass that's greater than 0.5. 1%. All right, now you guys all know what to do on the frisbee field. Are there any questions on this?
Have you updated your priors now?
Yeah, I'm gonna go different. Okay, my hypothesis for why I think it should be same, I don't want to spend a lot of time on this, but if you think about it, if there's anything other than a 50-50 chance that this lands on one side versus the other, they're more likely to be the same. Yeah, you can think about that for a second, or on your own time. But that is why I think that's the case.
But that assumes that every frisbee is distributed similarly. Official.
Yeah.
Okay.
Yeah, I think that, I mean, there are very, I can probably tell you more, but there's like very specific restrictions on, yeah, like, and I think these are all, yeah, theoretically. Maybe we need a model of the frisbee. Okay. Question, yeah.
Could you please explain the conjugate prior definition one more time?
Yeah, so conjugate prior means that when we have some likelihood model here, so given some distribution for the likelihood model, if we pick a certain type of prior, the posterior will have the same model class or type of distribution as the prior.
I see. So in this case, is our prior the beta distribution, and our likelihood is the Bernoulli?
Yeah, and then our posterior is
Is the beta?
Is the beta.
I see. So I'm confused then why we were looking at the binomial distribution.
Okay, so our likelihood of one data point given our parameter is Bernoulli. So our likelihood of just one time coming up heads, that's a Bernoulli distribution. Yeah. And it turns out that there's actually lots of conjugate priors, distributions with conjugate priors out here. Wrote binomial. All right, I'll make an ed post clearing this up because I want to make sure I get that straight. There's lots of distributions with conjugate priors. If you have a multinomial distribution, you may have heard it's the Dirichlet distribution, which is Mykel's favorite distribution. And Gaussian distributions result in other Gaussian distributions. Okay, maybe you've seen this meme before. It's the derivative operator trying to change e to the x, but it just can't do it because e to the x has the same derivative. So here's what I typically think of when I see that meme. All right, but sometimes we do actually have to make a choice, which is the point that I typically panic because I'm super indecisive. But no worries, there's a few different things we can do. So we could just take this distribution and use this distribution over theta and just take the expectation and use that as our theta. But if our distribution is multimodal, that might not be the best plan. So here in this case, if we take the expectation, we're just gonna end up with something here, which is like a theta that has a very low likelihood. So probably not the best choice. So the other thing we could do is just take the theta that has the highest likelihood. And this might not be unique. For example, in this case, it's here and here. We call this the maximum a posteriori estimate. It's just the argmax of our posterior distribution. And sometimes this is also called the mode. Okay, so that's maximum likelihood parameter estimation and Bayesian parameter estimation. Are there any questions on that? Yeah.
Do you have an example of like a non-conjugate prior?
I think like maybe not on the spot, but there definitely are plenty. Oh, you want to?
I have one. Maybe like a triangle density. If you start off with a prior that's shaped like a triangle, then the posterior will not be like that.
Yeah. Okay. I'll repeat what Michael said with the motions. If you have a triangle density, like the prior, the posterior might not be like that.
Okay, so it's just like if the prior, like the shape of the prior changes, like then it's not a conjugate pair?
Yeah, so if the type of distribution is different. A lot of times we can't, like, the system might be so complex that we can't even say what the type of distribution is. Like, it doesn't even have a name or a model class. And in that case, we need to do the previous thing we were doing, which was like that probabilistic programming, where we can only draw samples from it. Yeah.
Maybe just to follow up on that then, is the reason why we care about conjugate pairs just like, I guess because we have an analytical form?
Yeah, because we have an analytical form. The question was, why do we care about conjugate pairs? Okay. One last thing on parameter learning. I'm going to go through this kind of fast, but we should be careful about generalization. So many of you have probably seen this before. We could very easily overfit to a set of data, so that white model here fits all of the white data points perfectly. But if we sample more data from what is likely actually the distribution over this data, it's probably not going to fit them very well at all. And so we should be careful about this. And one way to check if this is happening is to have a separate validation set that we don't train the model on and use that to assess the performance of the model. So that's probably covered in lots of other classes, so I'm not going to say too much about it. But essentially there's like the holdout method where you just hold out a validation set to check this property. And then there's also a method called cross-validation where you select different subsets of your data and repeat this process multiple times. Any questions on that? Yeah.
Is that possible to fit to the data set that we have? For like a K-fold one, for instance?
Can you say that one more time?
Like for the K-fold cross-validation method that you're essentially going to validate over the entire data set, like would that overfit on that entire data set?
Well, so what you're doing is you'll only train on this part, and then you'll assess on this part. Then you'll just completely start back over again, only train on this part, and assess on this part. And then just to get an estimation of your validation error, you'll just average all of those. So it's never going to be training on stuff that it's seen before. Yeah.
I have a question to the slide before actually. So if we do maximum likelihood estimation and we take the maximum, or we just maximize of the posterior with Bayesian parameter estimation, does that give us the same parameters or not necessarily?
Not necessarily. So if you'll notice there's kind of this subtle difference here. It's written a little differently, but this is PD given theta, and this is P theta given D. And those maximums are not necessarily the same. So for one example, for like the frisbee flipping we were just doing, if we were to just do a maximum likelihood estimate, we would just divide number same by total number of times that we flipped. When we do the maximum a posteriori, we actually, do we get the same thing in that case? You don't know? Okay. Well, I think you would get something different, but I'm not 100% sure. But in general, they're not always the same. Good question. Okay. Okay, so the last step after we train a model is to validate the model. So I'll poke some fun at economists here. So maybe you've seen this joke before, but basically there's a story where a physicist, a chemist, and an economist are stranded on a desert island and they only have a can of food. And the physicist and the chemist devise these like ingenious mechanisms for getting the can open, and then the economist merely says, assume that we have a can opener. So it's kind of a joke for economists where people say economists just make lots and lots of assumptions. A lot of times it leads to these very useful models that we can use to predict things in the world, but we do need to be careful. And so if we just say, assume we have a can opener, that's probably not going to solve our problems. And that's just to say our assumptions don't really mean much if they aren't grounded in reality. And we're creating these models and we're going to use them to get all of our downstream validation results. And so if our model is wrong, then all of our downstream validation results aren't really going to mean much. So it's important that we kind of go one step further and validate that the model we just created actually matches what we were trying to model. To do this, we basically want to compare features of the model to features of our data to see how well they match. So one way we could do this is we could compare the probability density of our data to our model. So here we're showing a histogram of the data, and then the probability density of the model that we chose. We want to make sure if we're doing this that we normalize the histogram such that the area under it is equal to 1, so we can make sure we're making a fair comparison of two valid probability densities. And once we do that, we can just check visually how well they fit. So the one on the left here is a good fit. They seem to match up pretty well, whereas the purple model on the right doesn't seem to fit quite as well. We could also do this for the cumulative densities. So you can imagine kind of sweeping from left to right across this plot. And as we do that, we're accumulating probability mass that's under this distribution and checking how those match up. So that looks something like this. And so you can see for this bad fit, the CDF plots don't match up very well. And then for this better fit, they match up almost perfectly. We can also do something that we call a quantile-quantile plot, or QQ plot. So the way this works is we pick some value alpha, let's for now say alpha equals 0.1, and then we look over here and we look at our data and we say, what is the alpha quantile of our data? So what is the value for which 10% of our data is to the left of that value? We figure out that value. Then we look at our model and we say, what is the alpha quantile of our model? So what is the value for our model for which 10% of the probability mass is to the left of it? And we get this value here. And so then we take these two values, translate them over to this plot, where we put the model one on the x-axis and the true one on the vertical axis. And that forms 1 point on our quantile-quantile plot. And so then we can do this for a whole bunch of different values of alpha. And then we get a whole bunch of different points on this plot. And you can imagine that if the distributions were close to each other, the quantiles should roughly match up. So we expect this to follow the line y equals x. So you can see for this kind of bad fit, it's deviating from this line. There's a very similar type of plot called a calibration plot, where instead of plotting the q's, we're just plotting the alphas instead. So what we do is we say, for example, let's go to the 0.2 quantile of the model. So we can go over here, find wherever the 0.2 quantile is, and then look at our data and say, what quantile of the data is that? So maybe instead that's like the 0.08 quantile or something. So that's how we get this point here. We do that for all the points across this axis, and we get some line like this. And you can imagine, same deal, these kind of quantiles should match up if the distributions match well. So we want it to follow the line y equals x. So here's just a full comparison of all of these different visual diagnostics for one that fits well, where it does kind of follow these lines here, and then one that doesn't have quite as good of a fit. Is that a question? Yeah.
Is there a benefit to using the QQ plot versus the calibration plot, or is it just like they're telling like they're giving you the same sort of information, or is there like a reason why you would prefer to use one to convey something?
Yeah, that's a great question. So the question was, is there a benefit to using the QQ plot versus the calibration plot? They're showing very similar things, and they'll both show you if something's going wrong. Sometimes, depending on how your data is formatted, it's easier to calculate the calibration plot. And sometimes it's also just kind of different communities and different places use different versions of the plot. So like in machine learning, it's very, very common to see these calibration plots. Yeah. Yep.
Are you doing this with only the val data, right?
Great question. So the question was, would you do this with the validation data? I mean, you could do it with any data, but given what we were saying, you should likely want to do this with a validation set or a test set, like a separate set of data that you trained the model on to ensure that you're avoiding that overfitting that we were talking about earlier. So yeah, good question. Okay. So those are visual diagnostics. Sometimes we just want to like write down a number of how good we're doing. And so we can do that using some summary metrics. One summary metric for the PDF plot, or the probability density plot, is the KL divergence. So maybe you've heard of this before. It kind of gives us a measure of how close to PDFs are to one another. And so the good fit will have a low KL divergence, and the bad fit will have a much higher KL divergence. Just some notes here. The KL divergence is part of a much broader class of divergences called F divergences. You could read more about them separately if you're interested. Another interesting thing about KL divergence is it's not symmetric, and it's also not defined if the support of P is not a subset of the support of Q. So I just want to make sure you're aware of those. If you go to use KL divergence, you should make these considerations. But for the most part, I just want you to understand that KL divergence allows us to understand in one single metric how different two densities are. Okay, another metric could be for the CDF plot, or the cumulative distribution plot. This metric is called the KS statistic. And you can look at this formula, but really all that's going on here is we're saying that we want to know what is the maximum gap or the maximum distance between the two CDFs that we're trying to compare. So here it would look something like this. We can also summarize the calibration plot. So again, these are metrics that you'll very often see in machine learning. So we could do something like the maximum calibration error, which would be the maximum distance between our calibration plot and the line y equals x. And then the expected calibration error, which would just be the average over all of these distances. Okay. All right, so what if we want to compare multiple features? So here we were just talking about comparing one feature of the model to one feature of the data, but what if we want to compare multiple? So what these two plots are showing is it's the same data set in both plots, but these are two different possible models for this data set showing the contours of them. So just looking at these, which of these two models do you think fits the data better, the left or the right?
Right.
Right, yeah, the right. This one looks much closer to the data. However, if we only compare one feature at a time, so imagine that we took this plot and we just looked at all of the x values, and we just kind of marginalized over that and made a histogram of just all the x values, and similarly we took the same thing and did that with our model, it actually matches up pretty well. And if we do a similar thing with all of the y values, it again matches up pretty well. And then same thing for the plot over here. And so if we were to just look at these features individually, just kind of look at these marginals, we wouldn't actually notice that this model is not doing such a great job. And the reason for that is because we're not actually considering the interactions between features when we do this. So there's a couple ways to actually try to capture these interactions. One thing you could do is just kind of hand design a single feature that combines multiple features in a way that actually captures the relationship between them. So for this case, one thing you could imagine doing is kind of drawing this line across and then taking each data point and projecting it onto that line. So now we've made a single feature, one dimension, and if we do that and make the histogram and compare these models, then we can see that the blue model does not fit nearly as well as the purple one. Yeah. Sure. The question was, can I repeat what happened? So you can imagine we drew a line, maybe the line y equals x. We took each data point and we projected it onto that line. And then we were now plotting that new data set. And we did the same for our model. And we can see now that this model doesn't match quite as well as the purple one. Okay, there's one other option. So some of the summary metrics that we were talking about, you can actually extend to multiple dimensions. So for example, the KL divergence I was talking about, you can apply on multiple dimensions. So if we just do it in one dimension, again, we think that these distributions match quite well. But in 2 dimensions, we can see that this purple distribution has a much lower KL divergence than the blue one. Okay, and then finally, just really quickly, I want to talk about what if you have a conditional distribution that you want to compare. The kind of most general thing that you can do here is you just partition the conditioning variable into bins. So say we have py given x. We just divide up x and then just say, okay, x is the same in all of these bins. And we just make our comparisons in each bin individually. So if you're going to do this, you'd probably want to use more than 4 bins. We just did that for a visualization. But you want to keep the bins small so that x doesn't really have an effect anymore, and you're just comparing what's going on in the distribution over y. And so then in each bin, you could just compute the various statistics we talked about for these non-conditional variables, and then check how they're matching up. Yep.
So in this case, our conditional distribution model is continuous with x, I believe. And if we do a discrete bin over a range of x, which choice of x do we choose then for the model that we use for computing these metrics?
Oh, okay, good question. So the question was like, if we, this is like a continuous value of x, and now we have to decide what is our model, and our model is conditioned on x, so we need to input some value into our model. So in this case, we're showing 2 data sets, that we're just comparing 2 data sets instead of a model to a data set, so we didn't have to make that choice. If you did have to compare a model to a data set, you would just have to pick something sensible, so maybe like the average, like the center of the bin or something like that. Which is why you'd probably want to use more than 4 bins, such that your bins are small enough to the point where changing x doesn't have a huge effect. Whew, okay. Don't have too much time left. All right, so we could also validate models using expert knowledge. So if we don't have a lot of data, some of you may have heard of the Turing test. So this is kind of a Turing-like test where we would show an expert pairs of rollouts from the model and some rollouts from the data. And then we ask them to tell us which one came from the model and which one came from the data. And if they can figure out which one came from which 100% of the time, we probably didn't do a good job of making the model look like the data because they can tell that they're different. So if they get a high accuracy, we say it failed the test, we have a poor model representation. If they get a low accuracy, then, so maybe they can only distinguish it 50% of the time, then we can say that our model is pretty good because they're not really able to tell the difference between the model and the data. So some of you may have heard of the Turing test, which is like kind of doing this at a large scale with AI and figuring out if you can tell the difference between an AI and a human. Okay, so that's system modeling. We're going to talk about property specification next. So like I said, this is the second input to our validation model. And what we want to do is just formally specify what it is a system is supposed to do. So there's different ways that we can describe properties of systems. And what we're trying to do essentially is just describe the behavior of a system in some way that we can quantify. So one way to do that is to map system behavior to a real number. We call something that does that a metric. And another thing we can do is map it to a Boolean value, and we call that a specification. Sometimes we can kind of go back and forth between the two. So sometimes we'll derive specifications from metrics. So you could imagine, for example, an aircraft collision avoidance system, where our metric is the missed distance between our aircraft and the intruder aircraft, so this distance here. And then we could actually just derive a specification from this metric by saying the missed distance must be greater than 50 meters. So the metric, this is a real value, it's that actual missed distance. And then the specification maps that by saying it's true or false depending on whether our missed distance is greater than 50 meters. Okay. Sometimes we can also derive metrics from specifications. So we took this, we made it into a specification. We can actually take it one step further and turn it back into a metric by saying we want to know the probability that the missed distance is greater than 50 meters. So what is the probability that the specification is satisfied? Any questions on that?
Is the idea that all specifications have to be Boolean, like evaluatable, so just pure true false?
Yeah, the question is the idea that all specifications have to be like Boolean, pure, true, false. For this course, yes, like this is kind of terminology that we've coined for the book. The definitions vary, yeah. Okay, so we can also have metrics or specifications on single trajectories or full sets of trajectories. So for example, the missed distance was a metric on a single trajectory. So by the way, this plot here, we're plotting the relative altitude of the two aircraft on the vertical axis and the time to collision or the time to loss of horizontal separation on the horizontal axis for the aircraft. So what this is saying is as our time to collision approaches 0, we're losing all of our horizontal separation. So we want to make sure that we have this big vertical separation at that time to ensure that we don't collide. And so we'll take the missed distance when we've lost all of our horizontal separation. So when the time to collision is 0, we don't want it to be within this red region, meaning that we got too close to the other aircraft. If we have multiple trajectories, we could try to compute the average missed distance. So that's what's going on here. Okay, that's properties of systems. So we have metrics and we have specifications. And the plan for today, or probably part of Thursday, is to go through what are metrics, what are specifications. We'll talk very briefly about reachability specifications, but that's actually going to be an advanced topic for this course, so it won't be on the quizzes. Okay, but let's go ahead and dive into metrics. In this course, we're mostly focused on metrics for a stochastic system. So you've probably noticed we talk a lot about probability here. And so we really want metrics that summarize distributions. So when we were computing that average missed distance before, that was the missed distance over this whole kind of distribution over trajectories. So you can imagine we took our collision avoidance system, we've varied all of its initial states, etc., the various noise we apply, and we get a whole distribution over different trajectories that might occur, and we want to summarize this distribution in some way. So we have all of these trajectories. Maybe we have a metric over an individual trajectory, such as the missed distance. And then that, if we apply that to every single trajectory in this distribution, gives us a distribution over this metric. So it gives us a distribution over missed distances. And our goal is to basically come up with some nice, concise ways to summarize this distribution. So one thing we could do is take its expected value. It's maybe the first thing you might think to do to summarize a distribution. So its expected value is represented like this. You can think of it kind of like the mean, the average. It turns out that if your metric is a binary metric, so that means it's either a 0 or a 1, the expectation will be a probability. More on that in chapter 7. But it turns out expected value is often not enough to just summarize a distribution. So for example, all three of these distributions over missed distance, while they look different from one another, they all have the exact same expected value. So another thing you could do is take their variance, which kind of measures the spread of the distribution, and that would kind of distinguish these distributions from one another. Okay, another thing is that specific to this course, sort of, in safety critical settings, we often want metrics that are kind of conservative, that consider these like worst case outcomes, because if safety really matters, then we're really focused on kind of those worst case scenarios or edge cases. So in this case, a lot of times we're talking about these things we call risk metrics, which is just a metric for which higher values indicate worse outcomes. So more risk is bad. So one example would be if we kind of flip the metric, that missed distance metric that we were using, if we flip that around, so say we always start with like 2,000 meters of separation, and our loss of separation is then 2,000 meters minus this missed distance. So if we have a 0 miss distance, we lost all of our separation, we lost all 2,000 meters, and so that's bad. And then the higher the miss distance, the lower this metric will be, so the less risky. So all we did was just take the metric we were using before, flip it around such that higher is bad. And now we can see we still have the same expected value for all of these distributions, but we can kind of distinguish their risk using a few other types of metrics. So if we just look at these distributions, this one to me is kind of the most risky because, if I said if our loss of separation is 2,000 meters, that means we got all the way down to 0, we had no separation anymore. And so these are the things that are going to result in collisions. And this one has kind of the highest probability mass at these values near 2,000. This one's like a little lower, and this one doesn't have quite as much probability mass there. So this is our most risky, and this is our least risky. And one metric that we could use to try to distinguish that is something called the value at risk, or the VAR. It comes with a value called alpha that we pick. And the value at risk is basically the highest value that the risk is guaranteed not to exceed with probability alpha. So it's kind of actually just exactly equivalent to the alpha quantile of the risk metric. And you can imagine that the higher that this value is, kind of the more risky scenario that we're in. So a more risky scenario will have a high value at risk, and a least risky scenario will have a low value at risk. Another metric we can use is called the conditional value at risk, or the CVAR. Also comes with a parameter that we call alpha. And I don't want to get too bogged down by this equation here. It's basically just the average of all of the risk values that are above the VAR. So it's just taking the expected value, the expectation, of all of the values that are above the VAR. So kind of in a similar way, so it's the mean of the top alpha quantile of risks. And so in a similar way, this is would represent a high CVAR, and a lower least risky scenario would represent a low CVAR. And before I pause for questions, I just want to give some intuition for like what these are, because I think when I first heard of these quantities, they just seemed a little out there, kind of weird. So just some intuition here. So the value at risk, specifically we set, for example, alpha equal to 0.7, is the value that the risk is guaranteed not to exceed with probability 0.7. So we're saying we know with probability 0.7 that for sure the risk is not going to be higher than this value. And so if we can say that that value is low, we can feel good about it, and the higher it is, kind of the worse the situation. For conditional value at risk, one thing we could do is just like say we have this distribution over risk metrics. We could just take this expected value, but if we're being more conservative here, we're basically saying I don't just want the expected value, I want the expected value of the worst case outcomes. And so the higher this value is, kind of the worse the situation that we're in. Any questions on these? Yep.
So what are the worst case outcomes? The ones that are involved in specification? Or how do you define that?
The question was, what are the worst case outcomes? So we have let me go back here. So we're assuming that we have a distribution over our possible outcomes, and we're assuming that because it's a risk metric, higher means it's worse. And so the worst case outcomes are going to be the ones that are the highest.
So does that mean like anything that's above the expected value?
So for the CVAR, we take anything that's above the value at risk as the worst case outcome. And let me go over to a demo real quick, because that might kind of clear this up. So we have this kind of parameter alpha that we can control here. So I was been talking about it being 0.7, but this essentially controls like how conservative we want to be. So if alpha is 0.7, we're saying we want to focus on the 30% worst case outcomes. So as we increase alpha, you can see that we focus even more on like the tails there, the true like worst case outcomes. And as alpha approaches 1, we're just focusing on the absolute worst thing that could possibly happen. As alpha approaches 0, the VAR is going to focus or move all the way to the left of the distribution, Can anyone guess what the CVAR is going to be when alpha is 0?
Expectation.
Yeah, the expectation. Because when alpha is 0, we're considering all possible values of the distribution. We're starting at the 0 quantile and looking at 100% of the values of the distribution. And so now we're taking the expectation of all values, which is just the expectation of the distribution. Okay, so that's kind of how these go. So as I was dragging this around, the solid purple line is the VAR. The shaded region is the part that we're considering for the CVAR. And then the dashed purple line is the CVAR. So I'll just drag this a few more times so you can kind of get the idea. All right, so composite metrics is the next thing. So we were just talking about one particular metric. We were just looking at loss of separation. But what if we care about multiple things? And oftentimes these multiple things we care about are at odds with each other. So continuing with this collision avoidance example, maybe we care about the alert rate, so the number of times that the collision avoidance system tells the pilot to take some maneuver to avoid another aircraft. So the fraction of times it says to do that. And then maybe the collision rate, so the fraction of encounters that result in a collision. And ideally, we want both of these to be low. So we don't want to alert the pilot too often because they could get kind of annoyed and not want to do these maneuvers. But we also obviously don't want to have a high collision rate because that can be very dangerous. And so one tool we often use when we talk about these types of trade-offs is something called Pareto optimality. And the idea here is that a system design is Pareto optimal if we can't improve one of these metrics without making another one of these metrics worse. So let's look at this point here. Do we think that this point is Pareto optimal? No, yeah, okay, I see some shaking heads. No, it's not. We could get a point, for example, this one that has both a lower alert rate and a lower collision rate. Okay, what about this point here? Yeah, okay, see some shaking heads, yes. Yeah, this point is Pareto optimal. We can't make, for example, the alert rate better without making the collision rate worse. Okay, and then all points that are Pareto optimal trace out this thing that we call a Pareto frontier. And so the Pareto frontier is just the subset of all designs that are Pareto optimal. And what composite metrics allow us to do is basically create a single metric that allows us to select one of these points on the Pareto frontier. Because just by looking at our metrics individually, we can't really distinguish which one is better. Okay, so one type of composite metric is just a weighted sum of all of our individual metrics. So we assign weights to kind of relative weights to how much we care about each metric. So how much do we care about collision rate in relation to alert rate? And then we just take the weighted sum to get our composite metric. So for example, here if we had a weight vector that was said 0.8 is how much we care about collision rate, compared to 0.2 is how much we care about alert rate. We could compute that metric for each point on the Pareto frontier and then select the one that was the highest. Another type of metric is a goal distance metric. So here what we say is we have some goal point. A lot of times we select it to be something that we call the utopia point, which is what we would want in an ideal setting. So ideally we alert none of the time and we have no collisions. But this is going to be, kind of impossible to achieve. But we want to get as close as possible to it. So we just compute the distance from each point on the Pareto frontier to this utopia point, and we pick the one that has the minimum distance. And then you might be thinking, well, can I combine weights and also this goal metric? Yes, you can. There's the weighted exponential sum metric, which basically just kind of adds weights to this type of metric. How do we pick the weights? Preference elicitation. We're going to elicit some candy preferences, but we're going to do it next time.